Swayam Prabha. Digital India. Educated India.
Okay, so we're not going to look at money, we're not going to look at economics. I cannot even balance my checkbook. So I usually just accept there will be plus and minus from what I think it should have. Usually it's less than what I think I should have. That I think is a common problem to everyone. Okay, so we're going to talk about utilization now. Geologic utilization, that's what I do. And so I have good news for you. We are nearing the end. We have 2 more days to go. So you have 2 more days to listen to me. I apologize, but bear with me. So we'll discuss a little bit about CO2 EOR and carbon dioxide CBM, enhanced CBM, coal bed methane. And then tomorrow, I want to discuss a little bit about emissions control if we are doing CO2 EOR. One thing which was very interesting for me was about 5 years ago, 5 years? More than 5, maybe 7 years ago, I was visiting with the DGH and we were discussing CCS, and DGH was very clear. India cannot afford to do CCS. This was about 5 years ago. There is no policy, there is no interest from the government side to do CCS. The requirement at that time was to do CO2 EOR because of energy requirements. Energy is a commodity, much sought after commodity in India. And so that part has changed dramatically, with India being one of the more aggressive countries promoting CCS. And that has brought about a very interesting change. What we will look at here is to examine emissions control and the promise of emissions control or lack thereof with CO2 EOR. How much are we really getting control there, and how much are we adding to total overall emissions? So that's what we will examine going forward. So let's look at CO2 CBM. How does that really work? Just to bring us all in the same perspective, this is what a microstructure of coal looks like to an acoustic wave, to a sound wave. These are acoustic scans. This is about 40. This is 40 millimeters. And so it's fairly 4 centimeter size specimen. These are typically cleats. These are permeable pathways like fractures. Fractures in coal are called cleats. Coal typically has face cleats and butt cleats, and those connect up. All of this part, the matrix of coal, consists of bright and dull layers. These are very, very interesting nanoporous regions. So what we exploit here is that there is very large connectivity through these cleats here, and there is a very large receptor for various gases, for various adsorbent. Now, the governing factor for these is the following. We have permeability in coal that is governed by cleats. Now, the cleats transport gas molecules, and these gas molecules diffuse. They diffuse into the matrix, and these gases are tightly adsorbed in microporous regions. There is no incentive to release these gases unless you reduce the partial pressure. Okay, so that's the first part. So coal microporous region automatically has adsorbed gas in it. Most of it is physisorbed, and these can be 25 cubic meters of gas. This is at 1 atmosphere and 0 degrees centigrade per ton of coal for methane. So this is the amount of gas that we're looking at that is adsorbed into coal, into 1 ton of coal. So this is a fairly large amount. The amount of absorption depends on the maturity of coal. So coal has different types of maturity. The most immature is this brown coal, lignite. As you increase maturity, you increase the amount of cleats, it becomes more breakable. You have more bright layers in coal, and all the way up to anthracite, which is the hardest, most mature, most brittle type of coal. As you increase the maturity of coal, the amount of absorbed gas, the capacity to adsorb gas reduces. So if you have carbon dioxide, and the affinity of coal to various gases is different. There is a much larger affinity for carbon dioxide than for methane. And that depends also on the coal maturity. So the carbon dioxide to methane ratio is about 1. So it's really equally absorptive. But if you take immature coals, brown coals, your lignites, there is a difference of 10 times more affinity for carbon dioxide as compared to methane. And that's what we really try to exploit. So the injected gas, carbon dioxide injected into the coal, flows through the cleat system, and it's adsorbed into the cleat system and diffuses through the microporous region and releases carbon methane in the process. And that's really what we try to exploit. So we produce this released methane. Now, some of the things that we really don't understand is, we know as we put carbon dioxide into coal, it swells. There is a fair amount of swelling. There have been reports of plasticizing the coal, which makes a problem for any facility that might be existing. So the geomechanics of these desorption processes really are poorly understood. There have been successful projects that have exploited this with the Alberta Basin in Canada and so on. If you do CO2 ECBM, you get about 90% more produced gas of the total amount that's available. If you do pressure depletion alone, if you reduce pressure and promote desorption of methane, you get only 50% of the gas available. So there is a much higher recovery rate that you can get by using carbon dioxide. Now, obviously, as you increase depth, the cleats close because of the stress around it, and so your permeability decreases. You can't get gas to where it needs to be. Most of the wells that are producing coal bed methane are less than 1,000 meters deep, which makes it a bit of a challenge because you do not want that coal to be dug up at some point and have the carbon dioxide released to the atmosphere. What do the data look? This is the three-dimensional image. This is acoustic scan on the surface. It's pretty much a scan over here. And this is what the three-dimensional image looks like for some of the dipping layers for these bright zones here. If you examine what the carbon dioxide absorption looks like, this is absolute absorption. This is meter cube per ton as a function of pressure. These are not very high pressures, right? This is up to 100, 200 meters of depth. And so we have carbon dioxide absorption here, methane over here. There's a big difference between the two types of gases. And so if we supply carbon dioxide to the coal, we can get released methane back. This is really interesting because about 20 years ago or so, when we were starting with this, we did not understand the absorption process as well. This one was supposed to be much higher than everything else. And that was the simulation work that was done by some labs. And so with data like this now coming out, we have a clear path to allow carbon dioxide absorption to have enhanced methane production. Just by itself, we would not produce as much. It would only be if we were replacing one with the other. Okay, so that much about carbon using carbon dioxide for ECBM. There are affiliated challenges. One of them being water. In this case, there is no need to dewater the coal. If you're doing just methane production from coal, you have to dewater to reduce the pressure. If you introduce carbon dioxide, it reaches the coal in dissolved state, and the exchange happens through the dissolved state, which is really good news. I do not know how many ECBM projects are happening in India. I don't think there are. There's one through NGRI, right? You guys are doing something? SR is doing something. Okay. So SR also in Raniganj. Yeah, but I don't know how far ONGC got. I think they're going to start. Yes. So they have not started yet. Right. So that's the part which is a bit of a nascent stage in India. The challenge, the part which is really interesting is you do not have burning of coal. You get the energy through the methane that you're producing, which is much more benign for emissions. Rather than burning the coal, you have coal that is always still staying in place. So it is very appealing as a technology. At the moment, in most coal producing regions, this methane, which is co-produced when they are doing mining, is just released to the atmosphere. If you remember from the initial discussions last week, methane is a much bigger greenhouse, much more potent greenhouse gas, 30 times as potent as carbon dioxide. And so if we are reducing methane from coal that is being produced today and released to the atmosphere or flared, it has a dual purpose. One, reducing burning of coal. Second one, reducing the methane that is co-produced with coal to be released to the atmosphere. I do not know, and this is something which would be very interesting to have economics done on this part, to say if you replace, if you remember the last lecture, the big contribution to India's energy with coal, if you were to replace part of it with methane, how much of a difference would it make both to the economy of the energy production as well as the emissions control that you would get as a byproduct, right? Okay, so Let's talk about CO2 EOR, and that's carbon dioxide for enhanced oil recovery. The process is very simple, kind of. We have a production well over here. This is the separations facility out here and tanks that are accumulating tanks. And we have an injection well over here. In an idealized world, we will inject carbon dioxide, water, carbon dioxide, water. So this is what is known as a WAG, water alternating gas. That's the term that is used. And so what happens here is we are pushing this carbon dioxide out into the reservoir. This is our producing zone. As we go into this producing zone, we hit the zone of where the oil is. And as that happens, the carbon dioxide mixes with oil, makes it more less viscous, and sort of acts as a solvent to move the entire thing towards the production side. You produce both water and carbon dioxide and oil, take it here in the separations tank, and you re-inject. And you separate out the oil and gas, methane, hydrocarbon gases, and the hydrocarbon oils out here, and that goes to the market. The carbon dioxide gets reused, and the co-produced water goes into a disposal well further away. On a microscopic scale, you have something like this. You start getting oil that is left behind, the residual oil. Carbon dioxide comes in here, increases the fluid mobility, starts to flow more, and as it flows more, it moves with the pressure, with the flow, it moves more towards this region here. This is an idealized view. We don't think it works quite as nicely as shown here. Normally what happens is you get fingers of breakthrough, and once it's what's breakthrough means that it has breakthrough means that out here I have created a channel that's going through out here, and now I'm not washing anything through because there is a straight path over here, and I'm producing much more carbon dioxide and water, and much less oil that I really wanted to. So what we want is sort of a uniform flow that's pushing everything in front of the front. That's your injected front, and we expect it to behave very well and go uniformly. It never does happen that way, but it does work because there are enough examples of where these things work. The part that concerns us is if there are zones, for example, if there is something here, let's say we've broken through, but we know that there is bypassed oil out here and perhaps here, and we know we will never reach that oil because I have breakthrough. Now nothing else is flowing. It's almost like I've created wormholes for all of the fluid that I'm injecting that goes through here, bypasses everything else. We need to know that because then we can start treating that in a specialized manner and putting remedial action. So, site images, this is your pipeline metering. This is what brings the money in. Here's a typical pump jack. This is where production happens. These things move up and down, create suction. If you remember, for those of you who've grown up in a village where you have a pump for getting water out of the ground, this is very similar to that. This pump jack moves up and down. As it moves up and down, when it moves up, it creates suction in the well. Oil flows in. As it moves down, it pushes the oil out into the production side, and that gets pulled out. So that's your typical pump jack. Injection looks like this. There is really nothing happening here. All that's happening is the oil is, the carbon dioxide is supplied out here. You have blowout preventers and pressure measurement things here, and it's injected at some depth out here to flow into my reservoir. So that's sort of what the operations look like. There is usually no one sitting here. There is nothing here. These sensors that are contained here, this is your control board. All your sensors are out here from here. That feeds into the control board that communicates via satellite or some other technology to your station that's controlling everything. Power is supplied in this case with the solar panel. So maybe once a month someone goes in here or they go in there if servicing is needed. Otherwise, this is pretty much an open operation. This again, same thing, really does not require much babysitting. We have a couple of projects that we can look at. This is the Insala project in Algeria. There were 3 companies that got together, BP, 2 others, I'm forgetting their name. They had a gas production well. They produced gas over here, took it to the processing facility. In the processing facility, the product was stripped of carbon dioxide. That carbon dioxide was sent to the injection site. That injection site delivered carbon dioxide down dip and allowed pressure to build up for this gas to be produced. The formation had sandstones on the top, a thick interval of mudstones. This is the seal, and the structure was a very simple anticline. That means there is a bed that is sort of has two arms, and it is tilted up like this here, which means your gravitative separation has allowed a gas cap to be built, and that is what is being produced. Over here, this is your gas-water contact. That's the separation due to gravity difference, density difference here. And so the carbon dioxide that was injected was in the water phase. And the injection was 1.2 million tons per year down dip from gas-water contact. So that was sort of the operation here. And it was necessary because the produced gas had about 10% carbon dioxide. And that is a very large amount. So the process of doing this storage also allowed pressure to be maintained for this gas production. Now, the observations from the injection were very interesting. This has since been abandoned, mainly because there was satellite imaging. So this was the original surface of the Earth, and through satellite imaging, there was uplift in the area, and that gave cause to concern. Note, there has not been any leakage, nothing has escaped. But this amount of strain that was expected in the reservoir zone was not expected to propagate up to the surface. And so after storing about, I think, 3.8 million tons, this facility was shut down because of that strain. It is since subsiding because the gas pressure is reducing. But there is a very interesting set of data that is now being used to assess and learn from these challenges. As you can see, this thing was, and it's a good thing because everything was made public so that people can analyze the data for themselves. You have satellite data that provided the main information about uplift, and then there were geomechanical models that related the strain out here to strain propagation through these different layers to come up with the entire model of why there was a certain amount of strain being propagated to the surface. So that's sort of the typical study that happens. There's another field that's a very long-standing EOR field that's called the Rangeley field in Colorado. We have taken a lot of field visits there. We've done simulations for this work. Usually our petroleum engineers in the undergraduates studies go to this field and assess what the operations has brought us. We will look at the emissions from this field as well over the time that it's been operational. This is 78 cubic kilometers is the full extent of the reservoir. The average gross thickness is 116 meters. So it's a fairly thick interval. The effective thickness, that means the total reservoir interval, is about 40 meters. It's at a depth of around 1600 to about 2000 meters. Average porosity 12%, permeability 10 millidarcy, which is a fairly large amount. The carbon dioxide has been injected in this field since 1986 as a water alternating gas project process. So you have carbon dioxide, brine, you reach the miscible zone, and again it leads to additional oil being pushed towards the production well. This is exactly the same as the conceptual image that we had. The amount of carbon dioxide that has been stored is substantial. It's about 22 million tons of carbon dioxide. That happens because whatever we inject gets produced over here and we recycle, but this is not a 100% recovery process. Usually, when we inject carbon dioxide, we expect to leave behind 30 to 40% carbon dioxide is left behind in the formation. Depending on the formation, depending on the process, on the pressures, that's the amount that we leave behind that will not be recovered. So we count that as stored, and in the Rangeley field, we've stored about 22 million tons of carbon dioxide. So that's the thing where if you're separating out at the refinery, that's a mature process. We are stripping it, right? So when you look at this is the oil processing plant, and here you're putting the produced gas and you're stripping the unwanted gas from the saleable gas, and that is what is being recycled. That's a mature technology. What we're talking about is hard to abate places where your concentration is low, where you have you're either trying to capture from very dilute sources from the atmosphere, or where you have a large amount of gases that are mixed and you can't separate those. So this processing here for refineries is a fairly well established process. But you're very right to ask that question, and I think we will look at that when we examine emissions, because some of these operations happen with geologic carbon dioxide, which means that there is carbon dioxide that is present in some formations, and we're producing that from here, injecting it there, which means there is no emissions control, right? So as long as we are putting carbon dioxide that is coming from a source that would normally have been released to the atmosphere, then we are contributing to emissions control. If we are bringing carbon dioxide from a geologic source, which means it was sitting happily in the subsurface, was not coming out, and we put a pipeline in and we produce the carbon dioxide to re-inject, then we're not doing anything for emissions. It's purely an oil production.
Ma'am, one more question I have, that we are injecting carbon dioxide. So can this process be done with another gases or air itself?
Um, you can do it with methane, for example. There have been approaches and there have been studies to say you can either mix C1 and CO2, right, methane or some other light gas, and or a condensate. But remember, those are commodities that we need to sell. So that part we don't want to use, because if we can sell it, if we have excess that we're really not producing enough, that is economic quantity, yes, then that's the process where there are more recent advances, which they are mixing carbon dioxide with another hydrocarbon. Air you don't want to use because there are too many impurities. You would have to spend too much to make to have either nitrogen or some other gas to put inside, and you would need to strip it of all bacteria or anything, because bacteria love oil. So what happens is, if you have a very nice light oil, light meaning you have lighter components of hydrocarbons rather than asphaltenes and resins, the bacteria will eat up all of the lighter components. And what you will be left behind is just the resins and the asphaltenes, which are a much poorer product, which are much more difficult to produce, which are way more viscous than anything else. So you really don't want to contaminate and destroy your field that way.
Yeah, yes, madam. As you mentioned, there are different type of wells. Like we say, it is like a gas lift well and a gas injection well. So normally we'll be using the methane gas for the injection, and lifting the again the natural gas and crude oil. So, but we will not use the air. We will be using the natural gas again. I mean methane.
Yes. Thank you. That's an excellent point. So it depends on what we are producing and what we have available. Yes, absolutely. It's also a big safety concern. Yeah. Yes. Then you have oxygen, then you have other problems coming in with that. Yes, the objective here is not to store carbon dioxide. The objective here is to have more oil coming out. So this is on the tertiary stage of the recovery. So and we'll look through the stages of recovery and what you get. So this is on the last end. This is, you're trying to just squeeze out as much as you can from there. In Salah in Algeria. So if you look this up, it is very, very, it's talked about, written about a lot, because we have learned a lot from it. This was going to be a prime example of how to do this sort of sequestration. There were companies joining in. There were government funding that came in. It became a beautiful science project. And they added every type of sensor technology that was available at the time when they designed it. And so, short of fiber, so they don't have fiber, but they have everything else. And there were repeat seismic measurements, there were strain measurements, there were borehole data, there were all sorts of measurements, including INSAR, and INSAR was the one that gave the best knowledge. So it was very, very critical piece of work. This is what the production cycle looks like. This is from the Rangeley field. No, this is from Wasson field in Texas, but it's pretty much the same for every field. This is the initial oil recovery. So in green, we have oil recovery. In black is water injection. Blue is water production. And then red is carbon dioxide injection. So if you look at the oil production, you have very large production in oil. It's being produced. It's producing quite a lot. And after some time, it starts to decline. As it starts to decline over here, the company decides, well, we want really more oil. So they start injecting water. And water sort of drives the pressure. It doesn't act as a solvent. It just works to increase the pressure. As they put the water injection, that's what we call as secondary stage. Now, together with that, oil production increases. However, you have an additional problem that comes in. If you're injecting water, you have also higher water production. At some point, water production is very large and your oil production starts to decline. As you have that, then you start injecting carbon dioxide. So when you start injecting carbon dioxide, instead of this projected path, you start seeing a sustained recovery of oil. And that's a very typical sequence of production from a primary to a secondary stage, and if you're using carbon dioxide, to a tertiary stage. The amount of excess oil produced is over here in the green area. That's the amount that is produced. And if we say that we started this in somewhere out here, we've produced about 120 million barrels of additional oil through 2008, starting from here. Right? So that's a substantial amount of production. So that's why CO2 EOR seems very appealing. This is also the largest in-place CO2 EOR project, at least at the time of this article.